After you swap the x and the y variables, your goal is to isolate y. You want to remember that there's an understood parentheses when you have a square root or any root. The weakest operation then is the square root itself. So the first thing I need to do is square both sides. Then I'm going to have x squared equals, and the squared and the squared cancel each other out, and I have just the y minus 5. I'll be able to isolate my y if I add 5 to both sides. So that means that my f inverse function is x squared plus 5. Now, we are going to sketch both of these functions on the same grid. And I've been having you graph the x squared and the square root functions. When you graph x squared plus 5, that's your parabola who has a vertex at the origin. That's your parabola that goes through those 2 points as well, moved up 5 units. So the vertex is going to move up to, my pen stopped working. There we go. The vertex moves up to a y-intercept of 5. These 2 points are 1 unit horizontal, 1 unit up from that vertex. And if you want to plot more points, 2 units horizontal, 4 units up will give you some more of those points. And then draw that parabola. Then we want to, yep, go ahead.
Where did the 2 units come from?
What I was doing was I was thinking about how the parabola works. With the parabola, before you move it, it has its vertex at 0. And when you think about y equals x squared, if you go plus or minus 1 for the x, you get just positive 1. So when you go horizontally 1 unit from the vertex, you go up 1 unit to get to its y coordinate. If you plug in plus or minus 2, you get 4. So what this is telling me is if from the vertex I go horizontally 2 units away, I'll find the y coordinate 4 units above the vertex. I prefer to look at it that way than having to move 5 different points up 5 units. But you don't have to do it that way. You can do this any way that makes sense to you. If you need to first draw your y equals x squared function and then take all of those and move them up 5 units, you can do that. Did that make sense?
Yes.
Okay, great. The other function we're going to graph comes from the square root. So our original function, but I'm going to write it as the y instead of writing f of x. The parent graph is y equals the square root of x. So I'm going to start there. The square root of x has an endpoint at the origin. It goes through 1, 1, and it also goes through the point 4, 2. This tells me to shift it which direction? 5 units. I heard that. Yes, right, correct. That is right. So anytime a number is added or subtracted directly to the x, you're actually moving it the opposite direction. So if I move this vertex right 5 units, it's over here. If I move this point right 5 units, it's over here. And if I move this point right 5 units, that gets me over here. Now, do those look like they are inverses of each other fully? Do you see a problem?
Yes.
Thank you. Now, what we're focusing on with yesterday's classwork and today's classwork is we have an issue when we are working with the pair of functions x squared and square root. While they are inverses of each other, they are only half inverses of each other. For them to be full inverses, the parabola has to be restricted. Yesterday, I started you off with the parabola, and we came up with the inverse function. We actually first restricted the domain of the x squared function, and then we found the inverse and learned how to do that. If you start with a square root and you find its inverse function, you have to realize that your answer has to have a restricted domain. Then the question is, how do you restrict it? How do you figure that out? And do you remember the key point of restricting the domain? The vertex of the parabola is the place where you're going to split up the domain. And you need to figure out if you're going to use from negative infinity to the x coordinate of the vertex, or the x coordinate of the vertex to infinity. It's one or the other, but not both. If you graph the whole thing, you can probably see it better. Looking at the graph, which of these restrictions is the one we need to use? You got it. So visually, you can look at it and see that, actually, let me just do this, that this half is the reflection of the square root over y equals x. So basically what I did was for all of this work that was explained here. Let me go over to the answers and show you. And then the final answer for what is the inverse function for f of x. It's x squared plus 5 over a restricted domain of 0 to infinity. I have to tell you, that is one of the trickiest things to work with in algebra. The issue of the square and the square root not being perfect inverses of each other cause a lot of problems with graphing, but especially with equation solving. When you're graphing, you can visually see that something is wrong with those being opposites of each other. But when you're working with just trying to solve equations, you don't see that. And I want to tell you that this is the reason why when you are solving equations, that involve an x squared. For example, if I have, say, x minus 2 squared equals, I don't know, 5. You have to be careful because if you just square root, you will take something that is a full parabola and make it only half a parabola, and you're missing all the solutions that you should be getting. You have to remember that if you have an x squared, when you square root, and only when you square root, you have to put a plus or minus sign on that, or you will lose one of your solutions. If you are solving equations that have roots, you're starting with only this half. When you square both sides of an equation, you double what is there, creating more than you should have. Now, if you end up with a solution on this half, you're all good. But if you end up with a solution on this half, you get what we call an extraneous solution, because when you square both sides, you allow other things to exist that didn't exist. You actually are allowing x to have negative numbers go in the square root. And if you know why these two frustrating rules are there, this is why. The one you have to really keep an eye out for is not forgetting plus or minus. That is too easy to do. But when it comes to equation solving, if you always check your answers, then extraneous solutions show themselves. Okay, I'm going to scroll. And I am recording, so if you need to look back at this, you can go to the recording. And I want to go back over here. And now we have this one. Okay. We're going to show that these two functions are actually inverses of each other through function composition. So this is similar to yesterday's homework. G of h of x. I'm going to take my h of x function and I'm going to put it in here. Then I want to realize that all of this in the parentheses has to go into G's x. So what I'm going to do for that is I'm going to write out the G function but where I have an x, I'm going to have a parentheses. And then in that parentheses, I'm going to put the x over 2 cubed minus 1. And now what you're going to do is you're going to start simplifying. I have a 2 multiplied outside of a cube root. Inside of the cube root, I have this big giant parentheses, and I'm adding 1 to it. Do you see what happens when I do the add 1? When I add 1 to this expression, I can only bring together like terms. The like term is the other one that's just a number. And what happens? They cancel each other out, don't they? If I subtract 1 and then I add 1, I might as well have not bothered. Now I want you to notice that you do have a parentheses right here. And you have a third power. And right outside that third power, you have a cube root. When you look at your order of operations within an expression, if you have inverse operations back to back, they undo each other. So when I take this and I go cube and cube root, it's like, what's the point? And I end up with this 2, and then just the x over 2. And what does that simplify to? When two functions are inverses of each other, they go back to the original input. So basically, what this is saying is, okay, you guys, someone type in a number. Any number. Type in a number. 4. Okay. If I take 4 and I put it into the h function, and by the way, thank you for choosing 4. That's a nicer number here. 4 is divided by 2, so it becomes 2. And then 2 cubed is 8. And then 8 minus 1 is 7. 7 comes out of my h of x. It's okay. If I take the 7 that comes out of my h and I put it into the x coordinate of my g function, that is supposed to take me back to the 4. Oh, the answer is x. What I'm doing is I'm trying to demonstrate with a particular number what's going on. So if I actually replaced my x with a 4 at the very beginning, okay, now I can't get this. There we go. Stop doing that. Having problems of reading, not my mouse, read my pen. And it decided to stop listening to my pen. This happens too often and it's very, very frustrating. Okay, let me see if that'll work. Still not working. Okay, I will work with this. Give me a second. Okay, I can draw with my mouse. Now move the mouse over here, click on something else. Now let it read the pen. Read the pen, please. Okay, hold on a second. I am having technical difficulties and I don't know why it does this. It's listening to my mouse, but my mouse is not going to help me when it comes to writing. I can't get it to read my pen, and I don't know why. I have found the only way to change this. It finally worked. Often the only way to change it is to restart my computer and have it refigure itself. Okay, we're back on. Do you see that when I plug 7 in, I get 2 times the cube root of 7 plus 1? The cube root of 8 is 2, so 2 times 2 is 4, and I go back to where I started. It's important to understand that a pair of inverses do exactly that. If you put one of them inside the other, then you're causing your input on the original function to get an answer who goes into the inverse function and goes right back to where you started. So when an inverse function is when they are inside of each other, when you simplify, you get just x, which would be your original input. Now, we're going to do the same thing with the other way around. Because to be inverses, it has to go both directions and be correct in both directions. I'm going to do h of, and then I'm going to write g of x is 2 times the cube root of x plus 1. Then my h function is x over 2 cubed minus 1. So I'm plugging one function inside the other. Do you see the first thing that undoes each other? Right here, you have a cube root being multiplied by 2 and then being divided by 2. At that point, you still have the cube root of x plus 1 without the times 2 divided by 2. And you're looking for whatever pair of opposite operations are happening one right after the other. Right here, you want to see that this x plus 1 is being cube rooted, and then immediately it is being cubed. Back to back, you have opposite operations. Those cancel each other out. And then we're down to x plus 1 minus 1, and I get x. So Now, do you guys remember the Dr. Seuss book, The Sneetches, with stars on Mars? This is the perfect example of what an inverse is. So I can't even tell which one is the star. Oh, it looks like the yellow is the star on the machine because I see a star there. Whoops. And the red machine is the star off machine. This is what inverses do. They're like, ooh, I need a star. That's popular. They go in the red machine. They come out with a star. And then, oh no, stars are no longer popular. I need to go into the yellow machine. So they go into the yellow machine and it undoes what was done. Or you could look at it as they first go into the star on machine. They go into the yellow, they get a star and then go, that's not popular. So they go into the star off machine, the red, and the star is taken off. It undoes it. This silly situation is what happens when you compose an inverse function into another one. It is just such a brilliant, beautiful example of that. And just let that sink in, that that's what inverses are, that's what they do. The other thing that I need to go over with you today is a part 2 on exponent rules. And you have seen this first one before. I'm giving it to you on a day separate from the part 1 for a reason. So hopefully you're all with me. You're all taking notes. You're not just talking to someone next to you. Or maybe you have me on mute and you're just talking to someone else. It looks like that's what's happening to Shelby. Can you hear me? Shelby, are you there? Okay. It looked like you were talking to someone to the side and not being in class and paying attention. Of course, that's why everyone turns their webcams off, so that I don't know that they're not paying attention. But because you answered, I know you are. All of you should have your webcams on if it is possible to have them on. I need to know you're there and doing the work. Okay. Now, if I have x to the 5th cubed, I want you to think about what that is. That means x to the 5th is multiplied 3 times. And then what does each individual x to the 5th mean? It means x is multiplying 5 times. This is very cumbersome and I don't tremendously enjoy doing it, but I want you to look at that. I want you to understand that when you have one base to a power, it is telling you that you have 3 sets of 5 of those x's. See the multiplication of the exponents? Because people mix this rule up really, really badly with one of yesterday's rules. So I'm going to write down the rule. It is, if you have x to the a power to the b power, you simplify it by multiplying those exponents. The rule we learned yesterday, though, let me go over there. I want you to look at the difference when you have two separate x's that are multiplying, and you know how many there are of each, you're just getting one set of 5 x's, but your second set has only 2 x's. So you're only adding those exponents. Look at that picture, compare it to this picture, where it's now saying you have 3 sets of those 5 x's. And see the difference, so that you hopefully don't mix up those two rules. They are easy to mix up. All right, now, fractional exponents. We just learned a rule that said if I have x to the 5th power to the 1/5 power, that I multiply 5 and 1/5 together. What is 5 times 1/5? What is 5 times 1/5?
1.
You got it. Now, if you have x to the 1 power, you don't really need to write the exponent, so that's just x. Now, down here, I want you to look at the inverse operation. Putting something to a 5th power and 5th rooting something are exact inverse operations of each other. That means, from what we learned just a moment ago, that the result of putting two inverses together, one inside the other, the result is just the input variable. Now, this isn't a proof, but it's me trying to show you why this rule works. The fractional exponent rule is, let's see, if you have x to the power of 1 divided by n, that is the same thing as the nth root of x. And if I put this together, I can add on x to the power of m divided by n is the nth root of x to the m power. But, you know, if you think about it, it could go that way, but it could also go the other way. So let me just point that out to you. You could also look at it as the nth root of x to the power of m. Now, I want to point out to you that these next two properties are distributive properties. You're used to the word distributive property going to, you can distribute multiplication over addition. So I want to write that out there real quick. If I have, say, a times b plus c, I distribute the multiplication over the addition. But I want to ask you a very important question. What is the relationship of addition and multiplication?
Are you talking about
In general, what is their relationship?
Multiplication is basically like, it's just saying how many times you add specifically.
Exactly. Multiplication is telling you how many times you add. Hows. Can't. And how many times you add the same thing. Now, what is the relationship of multiplication and an exponent? An exponent is how many times you multiply the same number. So I want you to understand the distributive property of multiplication over addition works because of this relationship. Then likewise, there is a distributive property for exponents over multiplication. So if I have x times y to the power of b, that is equal to x to the b times x to the y. And I'm going to have to just quickly go to the classwork answers to show you what I wanted to. If you look at what I have right here, this is a little bit of showing you why that distributive rule works. Then the rule continues to work in all of these 4 situations. I showed you this one. I used different letters, but what you want to remember is exponents and roots are opposite operations. That puts them at the same PEMDAS level, and that means you can distribute an exponent over multiplication, and you can distribute a root over multiplication. Additionally, division is the inverse operation of multiplication. So just like you can distribute an exponent over multiplication, you can distribute an exponent over division. And then the inverse operation of both, the root and the division, also distributive property. And I have several examples here to show you why all of those work. But you want to see the set of those 4 the same way you're used to the distributive property of multiplication over addition. And you have used the distributive property of multiplication over addition. Now, I put it over here. You use this rule with subtraction. Shoot. Okay. I'm just going to write this down real quick then. I want to point out to you that you know that these 2 distributive rules work. You also know that if you have division, you can distribute the division. What I'm showing you here is a whole big bunch of stuff that will save you a lot of algebra pain if you understand the relationship of the distributive property in a bigger sense. Now, I will make a second video to post on top of this where I go over the examples here. You can also look at the answers to the classwork where I have a bit of a step-by-step guide there as well, but I'll do a video on top of it. I have to get you started on the testing, so